Wednesday, so we're going to talk about graphing today. Monday, we'll wrap up the graphing review, which really, we've only talked about graphing, and we've talked about that little bit in section 8.1, which was just kind of writing equations in that inverse variation form. But we're going to talk about rational functions, general rational functions, besides just having a number divided by x, or maybe x plus 3 divided by 2x minus 1. So they're going to be a little more interesting. The actual definition of a rational function, we said 2 days ago, was p of x divided by q of x. So one equation divided by another equation. P of x is a polynomial. A polynomial is really a big equation with a lot of powers. So x cubed, x squared, x plus 1. This represents the equation of a polynomial that we actually went over in chapter 5. A rational expression is one polynomial expanded divided by another one. So I could have x squared plus 3 divided by x cubed minus 4x squared minus 3x, something like that. So it's one polynomial divided by another, but it says they have no common factors. So there wouldn't be any canceling that I could do from one to the other besides the number of 1. And if it has a 1 in common, nothing really cancels out besides it staying the same. So we are going to see if we can try and graph these by finding important parts of graphs, besides just asymptotes and besides just plotting points from getting a t-chart. And below, there are some steps that we are going to use to help us find graphs or find information about graphs for these rational functions. I added the y-intercept, so if you could, like on the right side, place a little y-intercept in there. So the form of a polynomial is p of x divided by q of x. Sorry, of a rational function is one polynomial divided by another. Each polynomial, each numerator versus denominator of the fraction, actually finds parts of the graph for us. So the x-intercept, which is where the graph crosses the x-axis, can be found by taking or solving for the real zeros of the p of x function, which is the numerator. And we're going to find that by taking the numerator and setting it equal to 0. So an x-intercept are all the zeros, or the x values of the numerator. So if we take the numerator and set it equal to 0, we can find the x-intercepts. So the example here that's given is f of x equals 2x plus 1 divided by x. If we want to get the x-intercept, we're going to take just the numerator and set it equal to 0. And we're solving for x. So if it's an x-intercept, you're finding x. So Michael, if you solve for x here, what do you get? Yeah, what kind of one half? Negative, yeah. So taking the negative 1, dividing it by 2, how do you write an x-intercept? Chris?
Go to like x or negative 1.5, comma 0.
Right. So an x-intercept is an ordered pair. It's a point where the graph crosses the x-axis. So we'll be writing our x-intercept as an ordered pair as a point. So you take the numerator, you set it equal to 0. Now we have a point on the graph that crosses the x-axis. The y-intercept. Generally, how do you find a y-intercept in any of the equations that we've done? How do you get a y-intercept? So think about, what does it mean for a y-intercept? Peter? He said x equal to 0. So y-intercept isn't really taking the top and doing anything with it, but it's the whole function. So we're going to take the whole function and let x equal 0. Well, if I use this same example here, I'm changing f of x to y, 2 times 0 plus 1 divided by 0. Peter, what does that mean if you have 2 times 0 plus 1 divided by 0? It's undefined. What do you think that means about the y-intercept if it's undefined? Josh? It's the asymptote, so therefore there is none. Sometimes you might not have it cross the y-axis. It might just skim along the y-axis. So a y-intercept is found by using the whole equation, the whole function, and changing all of the x's to 0. So again, x-intercept, numerator, the top part setting it equal to 0. Y-intercept, changing all of the x's to become 0. So those are the intercepts. The other things we're going to find would be the asymptotes, which we've been talking about. It says the asymptote, the graph of f has a vertical asymptote, which we're going to call the VA, VA to abbreviate it, at each real zero of q of x. That's really the denominator. So p of x is the numerator. We set that equal to 0 for the x-intercept. Q of x is the denominator, and it says you're really setting the denominator equal to 0 to find the vertical asymptote, which is what you did yesterday, and hopefully you did that on your homework. So looking at this function, we have f of x equals 2x plus 1 over x plus 4. So the vertical asymptote is found by setting the denominator equal to 0. So the top is an intercept for x. The bottom is an asymptote, still for x, but now it's a vertical line. So that happens at -4. Make sure you have x equals. The x equals becomes a vertical line and not just a number 4, but a whole vertical line at the value of 4, or -4. So two intercepts, x and y, and now a vertical asymptote by setting the denominator equal to 0. The very last part that we've been talking about would be the other asymptote, which goes horizontally. And this has 3 conditions. And it depends on what type of equation you have based off the type of horizontal asymptote or where it's located. So it's not just simply, hey, take the denominator and set it equal to 0. So there's a couple of conditions that we have to look at. The first condition we already talked about yesterday. So it says if the degree of the numerator is equal to the degree of the denominator. Then the line y equals, we did A divided by C, is the horizontal asymptote. This is the one that we did yesterday. So this says the degree. What is a degree? Sadie, what's the degree? The exponent. Yeah, so the degree is the exponent of the equation. So it says if the degree of the numerator, which is really a 1, is equal to the degree of the denominator, then our horizontal asymptote, Sadie in this case, would be y equals 2. So when the degrees are the same, you're using the coefficients in front. So if I had a different function, just a second example. Let's say we had 3x squared plus 2 over 1 minus x squared. The degree of the top is equal to the degree of the bottom. So they are the same. That's that m equals n. So one power on the top equals the other power on the bottom. What's the horizontal asymptote in this case? Chris? -3. So you're taking the coefficient in front of that degree divided by the coefficient in front. So 3 divided by -1 would be -3. So you're taking that degree and you're grabbing the coefficient in front of it. So if they're the same, it's the coefficients. Number 2 says if the degree of the numerator is less than the degree of the denominator. So now we have a second condition. The first one equals. This one says less than. So the power on the top is less than the power on the bottom. then the line y equals 0 is the horizontal asymptote. There is no other asymptote. If the power on the top is less than the power on the bottom, it's always just y equals 0. So you'd have a line on the x-axis that would be our horizontal asymptote. So in this case, the power on the top is a 1. The power on the bottom is a 2. 1 is less than 2. So the horizontal asymptote is just y equals 0. No matter what. The power on the top isn't as big, so the number on the top is going to be smaller than the one on the bottom. If you're squaring something, you're getting bigger numbers. And in a fraction, if you have a small number divided by a big number, it gets really close to 0. So think a small number like 1 divided by a bigger number like 100 is really close to 0. The last condition, and there are only 3, says if the degree of the numerator is greater than the degree of the denominator. So now we're flipping what we just said above. And the graph has no horizontal asymptote. And the reason that happens is because now the number on the top is really big and the number on the bottom isn't. So now I have like 100 divided by 2 or 1,000 divided by 3. So the graph just keeps on going forever. It doesn't have an asymptote to stop it. The numbers don't get close to a value. So our value for y just gets bigger and bigger and bigger because you're squaring something on the top, but you're not doing that on the bottom. So we are going to see if we can try and interpret this information for every single graph that we do. So we're going to find the intercepts, we're going to find the asymptotes, and then we'll see if we can graph it. And we start off easy with an equation that has a 3 divided by x plus 2. So starting off a little easier, seeing if we can graph something like what we've been looking at. Your homework is divided up nicely so that you know all the parts that you have to find. But over here on the side, to graph it, we're going to get the x-intercepts and the y-intercepts. So split it up, x versus y. How do you find an x-intercept? So I know you might have to flip back and forth for right now, but how do we get an x-intercept, Peter?
For this equation, you take
So what would it look like? The x-intercept. How do you find an x-intercept? Chris? Right, we're setting the numerator equal to 0. So if this case, if the numerator is 3 and you set that equal to 0, what does that mean about the x-intercept? It's undefined. There is none because 3 doesn't equal 0. So it's not going to cross the x-axis. So the numerator equals 0 is the x-intercept. The y-intercept is when x is equal to 0. So now if we take that equation, we're finding y. That gives us 3 halves. So we have a y-intercept at 0 and 3 halves for 1.5. So x-intercept, numerator, only numerator, that's the p of x. Y-intercept, all x's must become 0. So now I have a point on the graph at 0 and 3 halves. The next part, find both asymptotes. So I'm going to make a little chart here just to kind of separate them as well. So we have the vertical versus the horizontal. The vertical asymptote is when we take the denominator and set it equal to 0. So in this case, it's going to be -3. What's the horizontal asymptote? So look at 2. Sorry, yeah, I know. Sorry, thank you. X equals -2. Thank you. So what's happening with the degrees in this problem for the horizontal asymptote? Nick? right? There's an x in the bottom with a power of 1. There isn't an x on the top. So if there's not an x on the top, it's not there. So the power on the bottom is bigger than the power on the top. So there's 3 cases. You need to look to see which one has that happen, where the degree of the numerator is less than the degree of the denominator. What does that mean, Chris?
Y equals 0.
That means y is equal to 0. So the power on the numerator isn't there. There's not an x. So that means it has to be less than the one on the bottom. So we're going to see if we can graph this information above. And then as it says, we're going to plot a couple of points on each side of the vertical asymptote like we've been doing. So going back to the top, we don't have an x-intercept, but we have a y-intercept at 0 and 3 halves. So on the y-axis, we have a point. We have a vertical asymptote at -2, so sketching that in at -2 on the x, and at 0 for y. So we have 1 point graphed. We have 2 asymptotes. It says plot points on each side of the vertical asymptote. So this is where that T-chart comes in. Look at your vertical asymptote and pick a couple of points. So right here's the vertical asymptote. Maybe we can use -1, or not -1, -3 and -5. Or you could choose -2 and -4. Pick 2 points over there. It's usually nice to pick one next to the asymptote so that you know what's going on right there. So that would be a -3. And then pick something that's not right next to it. So give yourself a little space in between. So -3 and -5, you could use -3 and -6. That would be okay as well. But get 2 of them. Yes. On the other side, again, pick a number right next to the asymptote. So that would be a -1. And then pick something else that's a little further away. So 1, 2, 3, maybe a 4. But try and get some points that are spread out so that you can see a curve happening in your graph. So this equation is nice because it's 3 divided by x plus 2. So you know the top's going to be a 3. And then plug in your -3. So 3 over -3 plus 2. Is that -3? Then do the next one. 3 over -6 plus 2. Yes, you're going to get fractions. Keep them as fractions. Do a little bit of guesstimating as to about approximate the value of the fraction. Cool. What did you get when you plugged in a -6?
3/4 or
-3/4. And then when you plug in a -1?
+3.
And when you plug in a 4?
1/2.
1/2, yeah. So at -3, we're up at 3. No, down at 3, not up. There's a little negative there, I just didn't see it. And then at -6, we're at -3/4. And make a curved graph. Try and curve it as you're connecting those branches, those points. For the other one, at -1, we're up at 3. And then I chose 4. You could have picked another number as well, but it's at 1/2 at 4. So that graph looks pretty much like the graphs that you would have seen on your homework, where you have those 2 that are diagonal from each other. Ava, what would the domain be of our graph?
The domain would be negative infinity, and then
-2 to infinity. And the range?
the range would be -infinity, 0,
0 to infinity. Questions? So the only true new part that we didn't talk about, yesterday was finding x and y intercepts, and now the fact that the asymptote is going to depend on the type of powers that you have. So let's see if we can look at the second one underneath. See if you can get those four pieces of the graph. So the x-intercept, the y-intercept, the vertical asymptote, the horizontal asymptote. We'll plot a couple of points to see what's going on with this graph. So there's not an x-intercept again, because there's just a 6 on the top. So no x-intercept when you only have a number on the top. If you have a variable on the top, that's when you'll have an x-intercept, but it's just a 6. 6 can't equal 0. For the y-intercept, when you make the x 0 in the denominator, you have a 6 divided by 4. 6/4 is 3/2. Make sure you're reading it as a point. So the vertical asymptote, Jack, if we set the denominator equal to 0, what happens when you solve for that?
That would be x plus 2.
Be careful. What would you do with the x squared? You took a square root to get rid of the x squared. What happens with the square root of -4? You can't take the square root of a negative number. It's an imaginary number. What do you think that means about the vertical asymptote? There isn't one. It's imaginary. We're graphing real numbers, not imaginary numbers. So there is not a vertical asymptote because there's a negative number that we can't take the square root of. Imaginary asymptotes don't exist. Yay. It's good. I mean, we could have imaginary numbers, but not imaginary asymptotes. And then, Jack, how about the horizontal asymptote? What's the degree? How does it compare on the top and the bottom? Yeah, the bottom is bigger. So that means your asymptote is at y equals 0. Yeah. So graphing, we have a point at 0, 3/2. Same intercept that we had just above. That's coincidence. They're not all going to be at 3/2. No vertical asymptote, so all we have to graph is a horizontal one at y equals 0. So since there isn't a vertical asymptote to kind of divide up the graph, it says to plot points on each side of the y-axis. So now we're going to plot some points on each side of the y-axis. Pick a couple. So maybe go with a -1 and a -3, and do the 1 and +3 on the other side. Or if you'd rather use 2 and 4, or 1 and 4, -1 and 4, -4. So if we plug a 3 in, we have a 6 on the top. 3 squared is 9 plus 4. We plug a 1 in, there's a 6 on the top. 1 plus 4 is 5. Because you're squaring a number, squaring any number, whether it's negative or positive, remains positive. So whether you plug in a -3 or a +3, you get the same y value. So again, plugging in 3, Negative 3 squared is 9. 9 plus 4 is 13, so that gives us 6/13. So when you go to graph this, we're going over to negative 3. 6/13 is pretty much a half. And then over to negative 1, you're going to 6/5, which is a little bigger than 1. On the other side, at positive 1, we're a little bigger than 1. And then at 3, we're around a half. Try and make this curved. And then it skims along your axis. This graph is totally different than any of the other ones we graphed because of that x squared on the bottom. It makes a mound. And it looks like a baseball mound or a little hill. The domain is negative infinity to positive infinity. What's the range? Peter, what's the range?
Would be 0, 3 halves.
Yeah, so negative infinity to positive infinity because the domain goes on forever. But the range would be from 0 up to 3 halves. That 3 halves gets a bracket. The 3 halves has a bracket because it's a point on the graph. So this is pretty much just filling out information. I'd like you to graph 7 and 8, and you can make your own grid on the bottom of the page. There's plenty of room on the back. But I only want you to graph 7 and 8. You're not graphing any of the other ones. Have a fantastic 3-day weekend. Make sure you keep your book at home.
Dude, I'm gonna be so mad if they like tack this on to